All right, we're back with another question, another problem. Let's get it going, see how it goes. So this question is going to be valid square. We'll solve with C++. All right, what do we want to say? Yeah, I guess we'll just get into it, see how quickly we can solve it. So, given the coordinates of 4 points in 2D space, P1, P2, P4, P3, P4, return true if the 4 points construct a square. Coordinates of a point P1, P sub I is represented as X sub I, Y sub I. The input is not given in any order. A valid square has 4 equal sides with positive length with 4 equal angles, 90-degree angles. Okay, true, false. P1, P2, P3, P4, true. So, constraints P1 length equals P2 length equals P3 length equals P4 length equals 2. And these points will be between negative 10,000 and positive 10,000. So I think this is a relatively easy question. This shouldn't be so bad, but more or less we can, more or less this gives us a, 4 points will always give us, I think, what they call a rhombus, and we can always get the length of each side of the rhombus. So that shouldn't be too difficult. We can do, we can sort of round robin the distance between P1, P2, P3, and P4. We could write a subroutine to do that. We'll can go ahead and write a lambda expression for that. But what we want to do is, so all those 4 lengths need to be the same, but there also is an issue of, so actually, yeah, I see why there are all these downvotes. What's interesting about this question is that the points themselves don't necessarily need to be the square could actually be on an angle if you wanted it to be. It doesn't need to be that's really interesting, actually. So you have a 90-degree angle between three. So it actually needs 3 points to check a 90-degree angle between the 3 points. How do you do that? That is a good question. Yeah. So basically, you have a vector. These vectors need to be orthogonal. So orthogonality. There's a way to check. Dot product for angle. Yeah, this is a pretty interesting between the vectors, right? This is what we want to use. So what's interesting is, right, to get a vector between 2 points, you take the difference between the points, the coordinates of the points, because there are actually 2 vectors to the points, and they take the difference between those 2 vectors. Dot product of 2 normalized vectors is equal to cosine of the angle between them. And you need to normalize the vectors in general. Yeah, that's pretty interesting. So, okay. So we have A, B, C, and D, and we'll use arc cosine. Vectors are normalized, then it's the arc cosine of A cross A dot B. So we can norm the vectors. Yeah, so we can, okay, let's do this. Pretty interesting question. So we'll use auto. We want to include vector. Kind of prefer to do this if I can. Remember to do that. Okay. So first we want distance, which is not really the distance, but the length. It's probably the length of a vector. Say v length. And we're going to take const standard. We're going to use tuples of int. Call it v. And we're going to say const auto xy, use destructuring to be v, and then we're going to return standard square root of x times x plus y times y. Right, that's the length of a vector. And then we're going to say v1 standard tuple int v1 is, say, get vector. So, yeah, we're going to get a vector tuple from two vectors a and b. We're going to say return, and this we're going to use. Yeah, we can actually put this here. That's fine. Return. It's going to be x and y. So b. So we're going to go to the right, which means that where you're going towards, you take the one that you're going towards, you subtract. You take those values as positive, and then you subtract the ones you're coming from. So we're going a to b. So it's going to be b0 minus b1, and a0 minus a1. And we're going to return those tuples. So we get these vectors. So we're going to say get vector of p1 to p2, v2, v3, v4 is p2, p3, p3, p4, and p4, p1. And then we're going to say check lengths. Or actually, yeah, we're going to normalize vectors. Check lengths. Vector. Int L1, L2, L1, L2, L3, L4. L1 is v length of v1. Can maybe put these things into an array, I guess. That might be a good idea. Maybe we should. That's not a bad idea. Call them V's. Okay. Check the lengths of each vector. Say vector lengths for, really this is a map routine we're going to do here, more or less. That's going to be for const auto reference p in vs. We're going to v length length of p, and then we're going to say x we're also going to say int check length equals 0. We actually want to check that they're all equal to each other. We could just do like something like a Boolean. First length equals false. And we'll say if not first length, or actually first length equals true. So it's not the first length, then we want to say x is not equal to check length, and return false. Otherwise, set first length equal to true or false. Update the check length equal to x. So this is kind of a complicated thing that we're doing here, but they want to check that they're all equal to each other. So we'll take the first. So we have nothing for check length. We'll make it 0 initially. We'll initialize it to 0, but we'd say if you're looking at the first length, then we should actually do it the other way around. We should do, if you're looking at the first length, I think semantically it's a little bit easier to think about. So if you're looking at the first length, then you're going to check. You're going to say it's no longer the first length. We're going to update our check length to x. Otherwise, you're going to check x against our check length, and if they're not equal, return false. So that gives us our length check as well as grabs our vector lengths. We can actually while simultaneously, actually it's better to do it this way, I think. Store that. Yep. And the vector lengths actually are not necessarily integers, by the way. These we're going to go ahead and use doubles. Yep, this actually is a double. So now we have our vector lengths. Now this is a tricky question because you might actually need to use like floating point arithmetic. Yeah, which is kind of annoying, but there's a way to do that. But we're not going to use it just yet. I'm not going to use it just yet. So so we get our v lengths. We have our check length logic. We push our lengths back. Now we want to check for 90 degrees. Normalize each vector. I guess for int I equals 0, I is less than vs dot size plus I, const auto xy equals vs of I. And we're going to say vs of I equals standard make tuple of, we're going to say x divided by v lengths of I, y divided by v lengths of I. So convert these to floats and then to doubles. So we normalize the vectors and then compute the dot products. So we'll compute the angle between each vector. Using some vector arithmetic. So now we can use arc cosine, which I think is, it's like C math, right? Okay, we really just need numeric. Can use just numeric, I think. Excuse me. Excuse me. We want arc cosine. A cos, yeah. So we can say double dp is going to be standard inner product of, actually, oh, whoops, can't do it that way. Okay, that's fine. So angle v angle, we'll say is going to be this function, it's lambda expression, const standard tuple of ints, say A and B. Auto A1, A2, or XY, or A, B, no, I can't do A, B. X1, Y1 equals A, and X2, Y2 equals B. We're going to say return a standard A cosine of the dot product. So it's X1 times X2 plus Y1 times Y2. Yes. Yeah, basically tie the values and multiply them and add them together. V angle. So we'll say. So now we have to do something kind of tricky here, where we want to check that the angle is 90 degrees. However, which is pi over 2. Couple things here. By the way, the arc cosine of -1 is 90 degrees. It's actually 1, right? Is it -1 or 1? So I was using -1 before, but actually, or I saw -1 before, but actually pi over 2 is 90 degrees, right? So, oh yeah, I see. -1 is pi, right? Arc cosine of -1 is pi. I think arc cosine of, that's fine. We can do pi over 2. That's fine. That works. That's okay. Hopefully that works okay. That works out all right. I think we can do it that way, but that might not actually work the way we'd like it to. Yeah, so we want to say check that all 4 vector angles are equal to pi over 2. So we'll say 4 int I equals 0, I is less than 4, or less than, really it's v's dot size plus I. We'll say if vs of I, or no, we'll do v angle is not equal to pi over 2, return false. And then at the end of it, we return true. And we're going to say v angle of v of I, vs of I plus 1, and this is going to be starting from 0, goes all the way to 4, and this is actually going to be v of I plus 1 modulo vs dot size, so it loops back around. Alrighty, what does this look like? How are we doing on time as well? I thought this was going to be an easy question, but we're already 20 minutes in here. Requires a const expression specifier. It's an error, huh? Okay. It's const expression, not a constant. Oh, okay. Okay. Can you just say it's not const? Static data member must be initialized out of line. That's kind of annoying. Yeah, I mean, that's something in C++ that I kind of find somewhat irritating. So I can't really have constants in my can't exactly have constants in my classes, something like that. It's kind of annoying. It's kind of annoying. Java actually handles that a little bit better, in my opinion. But C++, I don't even know how. I think you have to. It says you need to initialize it out of line, but like, where are you supposed to put that in a LeetCode problem? Yeah. That's fine. We can compute it each time. It's not good to compute that each time, but it's okay, I guess. It's okay, I guess. I don't know where I would want to put what the best place to put this would be. I guess we'll put it in. Oh, actually, we already have this constant. I forgot. We actually have this already. It's here, right? It's standard numbers, pi. I don't know if we have C++ 20 though. I don't think we have that. I don't think we can use that. We can do this. We can just calculate it here. Oops. It's a little bit wasteful. But we can do this. Yeah, calculating this every time we call the function is not great. Excuse me, where is this? Oh, okay, excuse me. Got the hiccups. Got the hiccups. 918. Okay. False, true. Nice. Nice. Okay, well, Yeah, we need to use almost equals routines. Okay. So where could this be false? All right. What's the length? Let's print it. Oh, these shouldn't be ints. These should be doubles. Yeah. I mean, in this case, actually, I think it should work, but it's all right. Should get all 4 of these lengths for starters. 0, 1. That's where it's breaking. Nice. And then also you need each of these angles. That's fun. Can calculate it twice, that's not a big deal. Okay, so so we got really the first length. Oh yeah, what? Vectors. So we get these vectors, and then you get the P1, P2, P2, P3, P3, P4, P4, P1. Alrighty. And these are integers. Now, yeah, they would be integers. That's fine. Now, the V lengths, first length, double length, check length is 0. X, so the first length was 0. That's interesting. That is not correct. Oh, these points are not in the right order. Ooh. That's awkward. Oh no. This shouldn't have been 0 though. Anyway. Oh, that's very awkward. Oh no. We have to figure out if it's a square, and we're not giving it in the right order. That's awkward. That is very awkward. Uh-huh. I thought this was an easy question. I was wrong. I was wrong. Oh boy. This is definitely not an easy question. This is far from easy. Great. Great. Wonderful. Wonderful. So what's interesting is P1, P2. Ooh, excuse me. This should have a length of this should have a length, actually. Why doesn't the first one have a length? What? Excuse me. Excuse me. Excuse me. Yeah. This doesn't have a length. For reasons that are beyond me. What is going on? What is going on? Okay, I don't know how we didn't get, how we got 0 for the first one, of the first length. X equals V length of P. Utterly confused. Utterly confused. Tuple, you do standard get 0 of P. and 1 of p. Let's see. What do we get here? Okay. Somehow we got 0, 0, 0, and 1, 0, 1. No, that's not true. Well, how did that happen? How did we get 0, 0 for our first? Oh, that's not correct. When we got our vector, oh, excuse me, that's why. Duh. I don't know how I managed to do that. Still, we should have got negative ones. Why is that is so confusing? What? What is happening? What? What? Oh, what? Oh, what? I think it should be A also, and B. Not. I think I've confused things. It should be. This is still really confusing. Oh no. It's B of 0. Oh man, that is just utterly confusing. That is the most confusing thing. That must be why. There are a few different ways you could move those things around. There you go. That's what it's supposed to be. It's supposed to be 0 to 1 would give you 1, 1, right? And then 1, 1 to 1, 0 would give you 1, 1 to 1, 0. 1, yeah, 1, 1 to 1, 0. You should point down. So that would give you x is 0 and y is negative 1, which is what you expect. Okay. Yeah, so that's all well and good. However, the order that these things are in, yeah, so this should be, these are x, y, and x, y, right? So for x, you need the second x, or the second x minus the first x. That's the second y minus the first y. Oh, that is just utterly confusing. That is just utterly confusing. Let's see. We want to. Never got this far. Right. So the problem we ran into is that these points are not in sorted order. Oh no! How are we supposed to do this? What? Oh man! Got to make a convex polygon of these points, convex hull of these points, and then check that the convex hull is a square. That's pretty much what we've got to do here. Oh no. Got to pretty much write this as its own subroutine. This whole thing here. Write this whole thing as a subroutine, and then use all 4 times 3 times 2, 24 different possible combinations. Deported 44 different orders for these points. And if any of those perform a valid square, then we're in good shape. Is there a way to ensure that the order gives us a square? I don't think so. I don't think so. Oh, this is too funny. Excuse me. Well, really, what we want, the order we want. Another way we can get the order is just check that everything to the right of the vector that we create, all of the other points are to the right of that vector. And do a right test. And I forget how to do the right test, but there's a right test predicate you can do. I always forget it. I think it has something to do with, Well, actually, I guess it's that simple. I guess you can just perform you get the angle, perform the dot product of the vector itself and the other point. Well, actually, it's not really a, no, dot product won't help you. You're going to what? I think it's the cross product you gotta use. Yeah, the cross product will tell you if it's to the right or to the left. The cross product between the two vectors, the projection, I think. Yeah, you have this other point and you have this vector, and you would project. You can take. So annoying. Basically, we've already normalized these vectors, but you would have a orthogonal vector to that other point. That points to that other point, either to the right or to the left, and then you can take the cross product of that orthogonal vector with your original vector. How do you get that orthogonal vector? Excuse me. That's another question. I mean, I guess you could do a. I mean, there are a few ways to do this, but I don't know. That's so annoying. I don't want to think about it. It's like cross products and dot products and things. Linearly independent is defined as non-trivial linear combinations of vectors that equals the zero vector. Okay. I think basically linearly independent is another way of saying that you cannot normalize. If you normalize the two vectors, they're not equal to each other. I guess another way. It's perpendicular to both. Same direction or have the exact opposite direction from each other. 0. Levi-Civita tensors. Wow. The deal with the cross product, though. So yeah, you can get rid of the sign calculation by using a dot product. What's the n? Is a unit vector? Oh yeah. Okay, gotcha. So you can take if you multiply these two, length of A, length of B, and the sine of this angle. But there's another formula for the cross product, which you can use. Yeah. Which looks like this. That's a nuisance. Make your head spin. Well, I mean, we really just want the sign of the cross product. Like we can use dot products too, I guess, to do this. So if the angle is between the two vectors, if you take 3 points, the angle between the two vectors, if that's less than 180 degrees, right? It's the arc cosine of the dot product of these two normalized vectors. Or we take the two vectors in between the points. If you take that arc cosine, also you can use, you can also, if you want to avoid using the arc cosine function call, then you can also use right, the cross product, which, and then take the cross product and the dot product are related by the following gram determinant. Oh. You would want to use, I guess, the square root of this then. Not the square root, but yeah, if you can get the sign of the cross product, that's a little bit more efficient than computing the arc cosine each time. But yeah, you can compute the arc cosine to get the angle as well. Oops. Yeah, this is a nifty thing. This is actually what I'm referring to here. So you can calculate this signed length of the cross product of the two vectors. Yeah. Yeah, this is exactly what I'm just thinking of describing. Another point of view, sine of P tells whether P3 lies to the left or to the right of line P1, P2. So basically what we would do is we would want to, we can select we can select the ordering of our points such that for all 3 points, right, for all like every how do you express it? So our sequence of points, if we select 3 points that are contiguous in that sequence, that the third point is always to the right of the line P1, P2, or the first 2 points. So yeah, so that would give us an order that we want. That would give us the clockwise order of our points. That's kind of what we could do. We don't need to. Excuse me. And actually, you'd want that since we want this to be the square, you'd want every other point to be to the right of each line. And then that gives us one of the vectors that we're looking for. Yeah. Then the question is, how do we order these vectors correctly? I'm tempted to just write this as a subroutine and then just go through all the 24 different permutations, right, of these points, these different possible orders of points. Or we could do that, or we could say could go through all 24 possible permutations and just do a depth first search and then run this whole algorithm as a subroutine. If any of that returns true, then it's a square. Or we can try to find the correct order by using these left test, right tests. Make sure all the for each vector, make sure all the points are to the right. Otherwise, that's not a vector we want to use. And but then we would get all the vectors we need, but then they would be in the wrong they would be in the wrong order. I guess they wouldn't be normalized, those vectors as well. This is also, I think this is a formula I want to memorize. I think you can just set the, this is exactly what I want. Yeah, we can just memorize this. It's x2 minus x1, y3 minus y1 minus y2 minus y1 times x3 minus x1. Signed length of the cross product of the two vectors. Yeah, it's a lot better than trying to figure out what the trying to perform the arc cosine routine. So anyway, distance of two skew lines not in the same plane, not intersected or not parallel. A pair of skew lines is a pair of lines through opposite edges of a regular tetrahedron. So I guess something through AD and something through C and C1. Those two lines, they're not parallel and they do not intersect. Yeah, interesting. You can have lines like that in three-dimensional space. Those are skew lines. Huh. Hung up on some things here. So even if we found all the vectors that we want, we still don't know the order. I guess it would be, could rearrange them until they're correct. You would say, basically you would say, you could start from any, actually you could start from any vector and it would, or any, yeah, I mean you can start from any point and then just apply the four vectors to get to the next points. Like, I don't know how to express it. You can, yeah, so you can, for each point, you can round robin each vector, or yeah, each possible pair of points, and get the vector between them, such that we get all the vectors around the outside edges. And then we want to actually produce. Well, the thing is, we could, I guess you could say, you just need to associate with that particular point that vector from that point, right? So each point will have a vector coming out of it. That satisfies what we described, right? Wherever all the other points are to the right of that vector. Yeah, you can brute force that. You can round robin that. That's fine. That's a little bit better than using a depth first search over all of the permutations. So the tricky thing there, though, I think would be, I don't want to use a hash map for this, but you can use a hash map to hash the, I think I'm going to make this a part 1. I think I'm going to make this a part 1 and then stop this problem and come back sometime tomorrow to this. Yeah, this problem is kind of pain in the neck, quite frankly. Yeah, so one approach is to use a DFS and just check that any of those give you a valid square. Excuse me, another check. Another way to do this is, I might just code that. That seems a little bit easier to code. Just run through this, make this entire thing a subroutine, and then just run that subroutine on all 24 different possible orders that you could have. Yeah, it might be a little bit easier. The other idea would be to, like I said, so you can find a more sort of brute force approach to find the different vectors that you want for each the square, where everything else is to the right, so all the clockwise vectors. But then you don't know the order of those clockwise vectors, so then you need to sort that out. So you could pick any starting point, and the tricky thing though is that I guess you could hash each vector to its starting point. You can hash those two together, and then you can use that to walk the square. The reason why I don't like that though is one, you still need to brute force all of the meaningful vectors, and that's the first thing. The second thing is that still gives you at least 16 operations, right? You would do 2 points, so you select each point, you select one of the other 3 points, and then you still need to operate. You select the other 2 points, and perform the right test. So you have 6. You have to do 6 up. You still actually end up with. You still end up with a lot of operations, right? You pick 3 other points. So 4 times you're going to pick 3 other points, one of the 3 points. So 4 times, you do it 4 times, 3 times, and then twice you need to check. So actually you still end up doing 24 operations anyway. So I guess it doesn't really matter. Sure, so I'll make this a subroutine then. Yeah. This is kind of involved, so we're going to move this all over here. All right, so some order of these pairs. P1, P2, P3. I mean, I guess you could just say, could do something like this. Yeah, okay. Something like this, I don't know. I don't really know. Just thinking, like, yeah, I guess you could. Sure, I suppose. Thinking about this here, how do we show all perform all permutations? Hmm. I don't know. Gotta think about that too. All the permutations, huh? Well, I don't even know. Where do you begin? Where does one begin? What you'd want to do, probably want to have like a bit vector or something. That's kind of what I was thinking. And you probably want this in an array, really. I kind of want to use a what do they call this? Like a splat operator. Yeah, a unpacking, unpack operator. It's kind of rare in C++, but that's fine. We don't actually need to use that. Oh, it's okay. We can use an array of. We can use an array of integers or vectors. Yeah. So interestingly enough. Oh, another way of doing this is like standard array of standard array of vectors of integers, and we'll just say array that'll be empty. We can say, I'm actually not really sure about this, you know, after all. Hmm. So we would select A and put A in the first position. And we loop through, we put B, we put C, we put D in the first position. It's confusing. And then or we put A in the first position and then recurse on what's left over. Yeah, you kind of do need a bit vector type of thing, bit set. The things you've already selected. That's a little bit confusing. Not particularly good at this with the permutations. I have a tendency to get this wrong. And I've done this so many times too. That's the thing that's kind of funny about it. Not funny, but interesting. Yeah, many times I've actually computed the permutations, but each time I tend to forget. Wow, we're already over an hour. Each time I tend to forget how to do it. Kind of do want to collect these into their own vector as well. Yeah. I mean, you can. Sure, I guess. Hopefully that makes sense. So we have the array, we have the points. We have the index. Sure. And we also have a bit set. We said we wanted to have a bit set. So let's try that. We'll just call that possible. I think they all start off at false. Something like this. Actually true. Something like this as well. And that has a reference. And we would do something like base case, if current index greater than or equal to 5, we'll say. Then we're going to ret or equals, also return, with check square on each of these points. Array of 0, array of 1, array of 2, an array of 3, something like this. And then we want recurse, permutations. So we're recursing on the other permutations. We're going to say for int I equals 0, I is less than 4, plus plus I, say if possible of I, and then we'll set possible of I equal to false. We will recurse. We will set array of I equal to, array of current index equal to array of current index equal to points of I, and recurse with each of these things, array points current index plus 1, possible an F, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So yeah, if it's possible, we'll set possible equal to true and update this to this points value, recurse. And actually, you'd want to update this to something else again. You'd return possible I equal to true. Afterwards. Yeah, I think that's fine. We don't really need to reset this back to anything. I think that's okay as well. Or something like this. Oh. Also, we need a few more things here. Should look like this. Initial index is 0. So I have these bit sets. Array points possible. Sure. Let's see what we get if we do this. Conversion from int to standard vector int. Oh. Initially this is just empty vectors, more or less. Oh. Okay. A few compilation errors. This cannot be implicitly captured. There are a couple things here that we're missing, huh? That's a funny way of expressing this. Let's not name a variable. Oh, I see. Oh, I think I understand. Okay. Yeah, I get it. I get it. I think that's what they're referring to. Cannot be captured by reference. Oh, okay. Can you capture by value? False. Nice. Interesting. Do I still need this? Interesting. Oh boy. Oh man. It's taking a while. This is taking a while. How about this? How many times does this get called? Oh. Okay. Well, that explains some things. I think it's got to be greater than or equal to 4. Might be the issue. Really? Starts off at 0. Give it a 1. Possible. Set that to false. Update the index to 1. I think it's greater than or equal to 3, quite frankly. Yeah. 1, 2, 3. No, I never call this. I'm so confused. What happens if we do this? Zero, 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 one. Okay. Oh. Oh, that's not correct. I see. See the problem. See at least part of the problem. And this should be just all true. Really. Why is that? Excuse me. So that apparently doesn't work. Okay. I think we just want set. Yeah. How about that? How about that? Runtime error. Nice. Okay. I think it's 4 is we're looking for here, by the way. There we go. And that works. Alright. Oh boy. No kidding. That's good. Very good. Uh-huh. Those are the different angles. So there we go. And how about the next couple of routines? We have 0, 0, 1, 1, 1, 0, 0, 12, 1, 0, negative 1, 0, 0, 1, and 0, negative 1. Alright, how do we do? Let's go for it. Let's see how we do. Almost certainly these are floating point errors of some kind. Okay, so yeah, I thought that might happen. Some kind of floating point error. Almost certainly. Just give me 1 second here, I want to check something. Kind of thought that might happen. I really didn't want to test this. Or I was just hoping it to just sort of almost magically pass the test cases, but this is a common thing you need to check for with, really should be floats, not doubles. And there is an order here. So 1, 1, 3, 5, 5, 3, 3, 5, 7, 7. So one of these returns true. Which one is true? Which one of these is true? So they're saying all of these should be false. This is not a square. Okay. I don't know. I want to like set up flag or something to know to print things in this subroutine. So if check square, and what? I could just print the order. Start with that. Also, I don't know what that's gonna print. Got it. It won't print what you'd like it to. These are vectors, right? So 0, 0, array 0, 0, 1. I can actually just do a we're gonna just save a little bit of typing. print this. So there are a few different ways that this can return true. 1 1 5 3 7 7 3 5. Back to 1 1 1 2 3 4. 1 1 3 5 7 7 5 3. And then 5 3 7 7 3 5 1 1. 3 5 1 1 5 3 7 7. Oh yeah, there's always going to be at least 4. If it's true, there's 4 different ways, right? 1, 2. How many are there here? How many different ways? 1 2 3 4. 1 2 3 4. 1 2 3 4. So actually, there's a lot of different ways, huh? 1 2 3 4. 1 2 3 4. So this is 16 already. And this is another 16. So it looks like every one of these returns true. Seems a bit odd. How? And this is also false as well, which is really interesting. And these points are, if you put it on a grid, you would have 1 1 1 1 5 3. So this is 1 2 3 4 5. 1 2 3 4 5 6 7. So rough estimate, by the way, 7 7. So 3 5 is here. 5 3 is here. Alrighty, so this is your parallelogram, it looks like. Now, for some reason, my algorithm seemed to show this as true, that this was, in fact, a square. So 1 1 to 5 3, A, B, C was 7 7, and then back down to 3 5 was D. So from here to here, here to here, here to here, here to here, these are the vectors that we picked. And somehow this returned a square. Now the lengths are the same, I think, but the angles are not. And I think that's the tricky thing here. How does that happen? I don't know about that, because I did have a check for the lengths. These must be wrong, these V angles. x1, y1 plus x2, y2, or y1. I think I did this wrong. I think it's x1, y1, x2, y2. Yeah, that's fine. And you have the dot product is the two x's multiplied plus the two y's multiplied, right? Am I crazy here? And yeah, take the arc cosine, and that should be a double. And what angle do we get for this V angle? And what angle do we get for this V angle? How did that happen? Was this not taken into account? I don't get that. What is going on? Huh. What is going on? I am so confused. Somehow these angles came out to be 90 degrees. I don't think so. I mean, maybe they are. Hmm. Hmm. 1, 1. 1, 1 to 5, 3 to 7, 7. This is apparently 90 degrees. Can we take pi over 2? What do we get? $1.5708. Okay. All right. I mean, it's pretty close. So apparently this is 90 degrees, right? So this vector from here to here is 5 minus 1. And 3 minus 1 gives you 4, 2. And this other vector is 2, 4. Seven minus 5 is 2, 7 minus 3 is 4, so we get 2, 4. Like an hour and a half in here. So 4, 2, 2, 4, yeah. These vectors are indeed 90 degrees from each other. Oh yeah, absolutely. If you take the dot product, so you can normalize both of these vectors first, the same amount. It's 16 plus 4 is 20. And then 16 plus 4 is 20. And you could take the dot product, you have 4 times 2 plus 2 times 4 is 16. 16 over 400. That's 4, 100, 1 over 25. Take the arc cosine of 1 over 25, and I think that's pi over 2. I think so. cosine of 0.04. Oh. Oh. Okay, we got 1.53. So that's not quite. Oh, you know what I think the problem is? I think I see what the issue is. These are not integers. Once you've, I think I see the problem. Once you've normalized the vectors, yeah, that's the problem. Okay, I thought there was something kind of. I thought I might have missed something here with the calculations. I did. That was kind of dumb. These really should all be just be doubles. And then to get the vector, we'll make these doubles. They really should just all be doubles all the way across. Yeah, it's kind of silly what I was doing. Still wrong though. It should be false, not true. So these v's should be doubles. These vectors should be doubles. And then v's double length, v length, double double. Get vector, integers, doubles. Divided by the v lengths, which are doubles. Okay. No, v angle is doubles. And let's try again. There we go. Okay. Yeah. Okay. I see. All right. Let's give it another shot. That was pretty dumb on my part. I kind of knew that too. I just kind of forgot. Where's the? There it is. That was really dumb on my part. Let's see if there's any other test cases they have for us. Show me what I did wrong. Oh, got it right. Okay. Not the most efficient way to do this. Well, we did it. Yeah, I think the other approaches are probably like 0 milliseconds or something. I don't actually know. It's probably a much more efficient way. I'm almost embarrassed because one, that took so long, and two, I made so many errors. Yeah, it just took a really long time, made a lot of errors, and didn't have a particularly good solution at the end of it. I guess we just assume, probably the other solutions assume that these points are, they're all integers, I guess, or they're given by integers. And so you really don't need to do, well, I don't know. there's probably better ways to do this that don't involve calculating arc cosine multiple times. Maybe that's why. Maybe that's I just have the arc there. I have to. Yeah, maybe that's the issue. Const double reference to pi. Let's try that. Let's give that a shot. That's probably not. It's probably not the only issue, but it could be. Let's see what happens if we do this. I'm curious. Is that any faster? Probably not. Probably not much. Not much faster. It's actually really slow. Slower. That's interesting. Wasn't expecting that. Well, let's go back then. Yeah, it's slow, man. I don't know. I think, I don't know. There are a few things. There are probably like quite a few different ways we can optimize this. We probably don't need to use all the different permutations. That's one thing. We also probably don't need all the permutations. Probably don't need to do all this math. There are probably a bunch of different things we can do, which are not coming to mind at the moment. But I assume there are different things, other things we can do to make this faster. I think it would be good to check out the discussion. I want to go to sleep though. It's time for bed. I think I had already. Oh, my phone is. Interesting. Yeah, let me go. I don't know, man. I don't know. This is This is okay, I guess. I guess it's alright, but the problem with this is yeah, I mean there's a few problems, I guess. There's probably a bunch of things. We should probably check out the discussion, see what other people came up with. I'm disappointed though. I had the right idea. This was correct. This was reasonable and correct. Just really slow compared to everybody else. I just needed to use doubles here instead of integers. Kind of just use doubles everywhere. Keep it simple. Yeah, that would have been fine. Yeah, this is okay. This is fine. This is fine. Not great, not amazing, but reasonable. Reasonable. All right. So thank you again for watching. Talk to you soon. I think maybe tomorrow I'll review like the discussion for this, and then also review some of the these other algorithm implementations. But yeah, for now, I'll say have a good night. Talk to you soon. Thanks for watching. Today was kind of rough. Today I spent a lot of time, but didn't really get too much done. I don't know, man. Part of me thinks like, oh yeah, I can fly through problems, but that's not really true. It's not really true. Some problems I can go through pretty quickly. Some problems I know well, but a lot of problems I don't know that well. A lot of problems would be I would really struggle. So yeah, all right. Thanks again. Talk to you soon. Take care.